All right, hello everyone. Today we are going to be covering the greedy, prodigal, and suicidal contracts at scale. I'm going to call suicidal contract, that was the paper title. I'm going to be calling suicidal contracts self-destructive contracts. I think it's nicer. All right. So brief outline of this. So we're going to do a quick overview of Ethereum and blockchains and how that actually works. And then we're going to go to what are called smart contracts and how they can be applied within the Ethereum blockchain, and I'll explain what smart contracts are as well. Then we're going to cover what makes these contracts greedy, prodigal, and suicidal. Then we're going to go into an interesting topic of vulnerability within smart contracts, which are called trace vulnerabilities. And trace vulnerabilities actually apply to a greater series of programs, but we're just going to look at trace vulnerabilities as they apply to smart contracts. And then we're going to talk about the algorithm that they used to analyze this, and then they did an evaluation of pretty much the entire blockchain, and we'll talk about results. And then there's discussion questions because this was for a class, but it's a really interesting presentation, so we're gonna cover it. All right, so Ethereum it's kind of like the Pepsi of blockchain right now. Where Bitcoin is the Coke, Ethereum's the second most popular one. It's a open source blockchain, and it has smart contract functionality. So for those who are not familiar, a blockchain is a big, I would almost call it a ledger. It's a list of transactions and proofs of work that says, hey, I solved this, here's proof that I solved it. And also there's proof of these transactions between users on the blockchain. So users on the blockchain have accounts, and there's two types of accounts. There's normal accounts, which just hold Ethereum or Ether, which is the actual currency. So one Ether is worth like $1,940, which is pretty good. So normal accounts hold Ether, and then smart contracts are basically programs that can do things with Ether that you deposit into the contract. When these smart contracts are in the blockchain, you upload them to the blockchain, and when you do that, you spend a little bit of the in-game currency, which is called gas, and you can use that to submit contracts to the blockchain. So smart contracts themselves are computer programs. They're designed for automatic control of a pseudo-legal event or transaction. And what that means is it's a transaction with some actual financial weight or official weight to it. Great example there, and we're going to use this example a lot, is a vending machine. So you take money, which is like the Ether, and then you take a request. So like I want a bag of Cheez-Its, and I want those Cheez-Its to be the Tabasco spicy Cheez-Its. And then in return, you get the thing, so you get the bag of Cheez-Its, and then you also get a bit of change as well. And that would be like some Ether back. And then, again, current value as of that epoch time, which was just about a week ago, was at $1,940. I don't know where it is right now. All right, before we keep going, does anyone have questions about blockchain? This is a lot. If you haven't looked at blockchain, I can explain that further. If anyone has any questions about that, I can explain blockchain further. Show of hands, who has looked at blockchain previously? Can everyone hear me?
Yeah, we can hear you.
Okay, cool. All right. So show of hands, I cannot see my Zoom controls. That's not good. Chat. All right. So has anyone worked with, okay, Norman, you worked with it. Awesome. Or you looked at it. That's really cool. Can you, if anyone is still confused about this, and if you would like to explain it more, can you reach out to me in chat privately, or publicly, or at all, because it's hard. It's a complicated thing, and I'm happy to explain it more. I'll wait for about a minute. Okay, so smart contracts are, again, it's code that can execute functions within the Ethereum blockchain. That includes transferring funds. That includes just random things. They have lotteries. They have like little games. You can make pseudo currencies on top of Ethereum. So if you wanted it to be worth $1 exactly, if you wanted your currency to have cash value, you can do that. They're made up of bytecode, very similar to actual executables in the real world, and they're run on the EVM, which is the Ethereum Virtual Machine. So kind of similar to how Java is run on the Java Virtual Machine. It's all run on this Ethereum machine. So again, any function that actually modifies the blockchain, whether that be you're changing a cost of something, requires some amount of ether to run. And that could come from you paying for it to run, or it could come from the contract's inherent value, because contracts can have a balance for how much money is in them. And what happens, and this is kind of the blockchain part of this, is contracts are run by miners, along with miners do two things within Ethereum. They will run and verify smart contracts, and they will also mine new blocks. And mining a new block is basically just you crack a really large pointless hash. And when that hash is cracked, they give you a certain amount of Ethereum. So, when the miners finish the contracts, and when the miners figure out like the correct output for the contracts, they publish that output, and then it's agreed upon by some majority of the entire network. And most importantly, and right here, these contracts are immutable. So once you upload them to the blockchain, you cannot change them. Does anyone have any questions about smart contracts? Because this is the this is a lot of the well, it's not prerequisite knowledge, but this is a lot of the primer knowledge for the actual paper.
I have a question.
Yeah.
I still don't really understand what the gas is.
Okay. Consider it. It has a 1-to-1 relationship with Ether. It is basically it's like an in-game currency. So you know how you can spend real life money on like gems in Clash of Clans, or like gold or extra lives in Candy Crush, or it's like a fake currency that they came up with that has like I think it's worth 1/100,000th of an ether. And you spend like 7 gas and your contract gets uploaded to the blockchain or something like that. It's just like a fake currency that they came up with to upload things. Does that make sense?
Yeah, I think so. Thank you.
Okay. If it's confusing, you can ask more questions. Like, no, like, we want discussions here. All right, does anyone have any other questions before I move on? Because this is when we start to break things. All right, let's do it. Let's break things. So, one of the most famous Ethereum bugs was the DAO bug. And the DAO bug, a DAO is a distributed autonomous organization. It was basically, Eric, gas is tied to the value of Ethereum. It's like I think it was 1/100,000th of an ether is like 1 gas. So it's directly tied there. If someone wants to Google it and tell me, I would appreciate that. I didn't have the exact value. Yeah, no problem. So DAO is the Distributed Autonomous Organization. It was basically a large governance network that people could use for their own contracts to make sure that like things worked well. Basically, it was a giant decentralized library. The logo of it is in the top right corner. Within that library, there is a split function, which split contract, basically, there's more minutia to it, but it split contracts between a majority and a minority. And it had a recursive call in it. So the split function had a recursive call in it. What they had was called a reentry bug, where you could recursively call it again and again and again, and take funds from it before checking its balance. And what that meant is you could just take funds directly from the balance of the contract. So a criminal, a hacker, or a cyber criminal, let's call them a cyber criminal because we're hackers. A cyber criminal managed to call the DAO function split within itself and steal money. The result was 3.6 million Ether was stolen. And that doesn't sound like a super big deal. But in reality, that is currently valued at $7 billion. $7 billion, not 7 billion Ethereum. And the actual effect of that was people didn't really like that at the time it was $150 million. So people didn't like that $150 million just went whoosh. So what they did was they hard forked the entire blockchain. And a hard fork means that the entire community split into two, where the no DAO community right here, the green line, said we're going to reverse the effects of the DAO bug, and they continued with that, and that's the current Ethereum that's worth $1,900. And the one that kept the DAO bug was Ethereum Classic, and Ethereum Classic is only worth $55 right now. So in reality, the 3.6 million Ether that's stolen is only worth around like 150 something. I don't remember. It's worth 55 million Ethereum Classic. So it's still a ton of money, but it's nowhere near the strength that it could have been. Or it's nowhere near the effect that it could have been had everyone not agreed to remove it. So what does the DAO actually have to do with this paper and greedy prodigal and self-destructive contracts? So for that, we're going to go to a vending machine example. So we've got a vending machine. 1 second. We have someone from not Illinois who might want to hop on, and this is a Illinois-only Zoom call. There are not 25 of us, though. Do you guys mind if we all hop over to Security Voice in Discord? Does anyone have any objections to that?
Yeah, that works.
All right. I'm going to end this call then, and we will hop over. Can everyone still see me? Oh, wait. I am using my camera for the actual thing. Can everyone still hear me?
Yeah, it looks good.
All right. Discord's picking up. Sweet. Let us continue. So, for how this is, how we found failures and vulnerabilities within this, we're going to use the vending machine example. So the vending machine example is pretty famous because it's a great example of how a smart contract actually functions, because it's a pseudo-legal agreement because you get stuff. So let's go through it. So first thing here, we've got Ether, so money in the context of a vending machine, plus some input. So I used QR codes. These are all scannable. Scan them at your own risk. They are not viruses. They are just really bad memes. So you send it into the vending machine or smart contract, and the smart contract produces, it processes the input, and then it returns an output and or some Ether. So if you're transferring it, it might return some Ether. If you're just trying to do a print function or something mundane, it could just return an output. And then lastly, the smart contract owner, as long as they have it set up properly, can pull the Ether stored in that smart contract back to their personal accounts. The gain is too high on my mic, sorry. So they can pull it back to their accounts. Now let's talk about the first vulnerability here, greedy contracts. So what's going on here is you've got Ether, maybe. Hopefully, it's a 0 Ether transaction, which means you don't have to pay any money, and then this happens. So you've got Ether, maybe, and some malicious input. It goes into the smart contract, and then the result is that you might get an output, you might get some BEPS or something, it doesn't matter. But after you send this malicious input, you can send money in, and you can send code in, but you're never going to be able to transfer funds out of the account anywhere. So no funds can be transferred, and the owner can no longer pull Ether out of the contract. So this contract is greedy because it just takes in money and money and money and money and money, but doesn't do anything with it ever. So prodigal contracts. The DAO bug was a prodigal contract, which is why I mentioned it. So how prodigal contracts work are you take Ether maybe and some malicious input, and you might get an output, but it's not relevant. The contract owner could still take funds out, but that's not really relevant. The big scary part is that funds can be transferred to arbitrary addresses. And that's not necessarily a good thing. Because you could have some funds going to Texas, you could have some funds going to Idaho, and you could have some funds going to Illinois. And if they can go anywhere, they can all go to one person's account. And the last one is self-destructive contracts. And what happens with that is you take Ether, maybe, hopefully not again, and then you take some malicious input, then you combine them together, and you get an explosion. So there's two commands. The self-destruct command in Ethereum actually just removes the entire contract from the blockchain. It removes the global variables, it removes the code, it removes everything completely. So there's a few caveats to the vending machine example. The vending machine is a black box, whereas in actual smart contracts, you can see the bytecode. It's all public because it's all part of the blockchain. Bugs can appear in both of them, but because smart contracts are immutable, you cannot change smart contract code. You also can't complain to support in Ethereum. Because it's decentralized, there's no such thing as support. If you screw up, that's on you. If you lose $10,000 in Ethereum because your contract was just giving away money to whoever, that's ultimately on you. No one's going to say anything about it. Additionally, attacks on vending machines are not scalable, whereas in the Ethereum network, they are scalable. You could screw one thing up, for example, a bug that I'm going to mention in a second. You could screw one thing up and just like a bunch of people's contracts immediately become greedy. And then there's physical limitations. With smart contracts, it's all in like the network, and it's all online, and it's decentralized. Whereas with vending machines, you can actually like go and grab cash from those vending machines, but you can't do that. You can only do that so many times in a day because there's only so many vending machines nearby. So, the parity bug is the combination of all of these things. So there was someone named DevOps199 who was supposedly a newbie in Ethereum, and they are screwing around. And this newbie decides, hey, I'm going to just start sending kill commands and self-destruct commands to random contracts. And they sent a kill command to the parity contract library, which was a very, very popular contract library that was used to for people to just like easily make transactions. So instead of having to write your own function, you could just call a parity function. There's a problem with that. They didn't set it up safely so that there was one function called release, which would automatically release all of the Ether in a smart contract back to the creator of the smart contract. That was not secured at all, and it was only one instance of it. So when it died, the whole thing disappeared. The whole parity contract disappeared. Someone was able to kill the parity contract because anyone can call these functions. So the second they called this function, the whole contract died, and $300 million instantly became greedy. It just it evaporated. No one could ever use it again because there was $300 million worth of function developers using this parity library to remove their money and to transfer funds. which is a little ridiculous. So DevOps 199 went onto GitHub and submitted a bug saying, anyone can kill your contracts. I know because I just did it. And the line there is, I accidentally killed it and simultaneously evaporated $300 million. So, does anyone have any questions about greedy, prodigal, or self-destructive contracts? I can take like a little bit of a break here. Does anyone have thoughts about this so far? Does anyone have general thoughts on blockchain and blockchain security?
Wait, can you hear me?
Yeah.
Is there like an equivalent of this in Bitcoin?
So there is a Bitcoin scripting language, yes, but it is very, very restrictive with the purpose of they don't want things like this to happen. So it's very, very, very restricted and small.
Thank you.
No problem. All right, if no one else has any other questions, I'm going to go ahead and keep moving in about 20 seconds. All right, let's keep going. So, discussion question, we can skip that because this is not a class. So, trace vulnerabilities is the next thing we're going to cover. And what that is basically you've got 1, 2, 3, 4, now your contract is no more. And the joke there is that trace vulnerabilities use what's called an execution trace, which is sequential invocations of a contract. So, there's two main categories of bugs that'll be violated here. Safety and liveness, not liveliness. And there's just a bunch of other information here. What matters is there's two main categories of bugs, and execution traces are multiple repeated invocations of a contract, which means you run it once and then you run it again under different circumstances, and then the vulnerability happens. So there's some important Solidity functions to know. Send, call, and transfer are like basically the syscalls, so like the lower level functions that do certain things within Ethereum. That's and specifically Solidity, which is the programming language that Ethereum uses. So send, call, and transfer funds. Then suicide and self-destruct, remove the contract completely. Think of that as just the contract ceases to exist on the blockchain. And then stop and return are functions that instantly stop all execution of the contract. So safety violations. Basically that's during execution, nothing bad happens. So there's formal definitions of prodigal contracts and suicidal contracts. All you need to know is that to detect a prodigal contract, you want to reach a call, transfer, or send instruction with the recipient being the account that called it, the attacker, without before reaching a stopping instruction. The other option is to reach a self-destruct instruction or suicide instruction with the recipient being the caller, because sometimes if the recipient is the caller, when the recipient is the caller, all of the ether goes to the caller, or the person who, the attacker in this case. With suicidal contracts and self-destructive contracts, a contract, if you can find a suicide or self-destruct instruction as the final bytecode of this execution trace, then you're golden and the contract will blow up. And then liveness violations are something good must eventually happen, I hope. And that's with greedy contracts. And to find those, you want to find execution traces up to a certain number of invocations that never reach any transferring instructions, aka call, send, or transfer. Does anyone have any questions about the actual bugs here? I know it's a lot. I mean, it's a lot. So if you have questions or if you just want to talk about it, feel free to discuss. And again, I will wait a minute. So, recording again. Great question. The question was prodigal contracts, again, how they're working. So, a prodigal contract, basically, you reach a call instruction or a transfer instruction with the recipient being some whatever address. Because if the recipient can be whatever address, you can set that recipient address to yourself. So a lot of these are actually just, pretty mundane, and a lot of like mundane contracts can be called prodigal because they could just have transfer functions in them where you can transfer to an arbitrary address. But some of them are just like legitimately buggy and are just leaking ether, which is why it's a vulnerability class. Any other questions? Good question, by the way, Justin. All right, if there's no other questions, we will continue. So MAIAN, and this is an algorithm. So MAIAN is how trace vulnerabilities are found, and it's a symbolic analysis tool, which is used to symbolic analysis. It's a field of binary analysis and application analysis that you're given a start state and you're given the code for the contract, and it tries to figure out what the desired end states are and what you would need to do to get there. So it reasons across. So MAIAN was designed to reason across multiple contract invocations. So multiple executions of the same program, and also multiple blocks of the blockchain, which is pretty cool. And it uses pretty traditional symbolic analysis and execution techniques, which is you run all the options. So if you get to a branch, if you get to an if statement, unless the if statement can be concretely evaluated for sure, it forks the program and it splits the program into two, so that it runs the true option. You can't see my hands. It runs the true option, and then it also runs the false option. You guys can't see me at all. Those of you on YouTube, it runs the true function, and then it runs the false function. So it forks the contract. And it's also limited by traditional symbolic execution. So that includes something called path explosion, where if there's like a loop, and there's lots of if statements within the loop, if the loop goes 100 times, you could have 100 different forks. And that can kind of start to blow up the analysis. And then another thing that you can do is you can fork the entire system. So in this case, you can actually fork the entire blockchain to see what would happen. And that'll be covered in a bit. So execution path search is really the core of how it works. And you want to, again, the goal for like a prodigal contract is you want to find what causes the call function or the transfer function. So with that here, you've got your function, and it comes to an if statement. And if that statement resolves to be true, you go to your transfer function. And if that statement resolves to be false, you're going to not the transfer function, and you're going to a stop function. So it's done. So with concrete evaluation, say X is true and Y is false. And you're trying to see if X and Y, not Y, is true. That you can concretely evaluate that because those things are all constants. So you evaluate it, and then you 100% take the green path. So you 100% go to the call because you know that it's never going to go to stop. But if you don't know what X and Y are, or you don't know what even one of them is, you have to split it. So you have two processes now, and you have one that does the call and one that doesn't do the call and goes to the stop. And you want to try to find what reaches the call. But that comes in terms of just parameters. So in detail with the execution path search, when you find a concrete branch, you evaluate that concrete branch, and then you take the result. And that helps limit the search space. And this is doing what's called a depth-first search. Does anyone know? Does anyone want to explain what a depth-first search is? Come on, I know a few people who know what a depth first search is.
I can try.
All right, go ahead.
So a depth first search goes to well, I'm not sure what it does here, but I know that it goes through each path, like till the end of each branch, instead of looking at branches that might execute in parallel. Does that kind of make sense?
Yeah, that's actually a good way to explain it. So another kind of way to say it is it tries to run as much of the program as possible before like moving on to a different attempt. It's hard. I mean, depth first search in this example is hard to kind of explain just because it doesn't seem like a graph because it's execution calls, but there's a way to represent it as a graph. So back here. So let's do depth first search on this. We go start here and then call into the if, and then we don't know what X and Y are, so we go to the call and we go to the stop. And then we finally start returning and we actually finally start evaluating the results once we reach this call or once we reach this stop. We don't evaluate the result at function because that's pointless. So that's kind of what's going on if anyone was confused. But Akshuna, you did a really good job explaining it in formal terms. So props to you.
I'm just gonna correct you real quick. Sorry, the pronunciation of my name's Akshun.
Akshun, thank you. Sorry.
Yeah. No problem. But yeah.
So then memory management is really interesting because Ethereum and the blockchain doesn't really do memory management like you would think. It's not just it's almost all stack space, and any non-stack space is read from the like main blockchain and then locally mapped, I believe. Don't quote me on that, please. I've been doing this for a while now, and it's still pretty magical and still pretty confusing. So additionally, external calls, so anything that calls a different function, is automatically marked as symbolic, which means MAIAN is interprocedural and not intercontract. And then lastly, there's pretty standard stuff. So data type evaluation using an SMT solver, non-deterministic inputs, bounding the search space with maximum call depths, maximum nodes, max analysis time. And then pruning with memoization, which is a thing that a lot of people will learn in CS 374 or ECE 374, I think, as well. And if you don't have to learn it, don't, because it's hard. It's hard and confusing. And then the one interesting thing that's kind of unique is a flagging violation. So if you see a safety property being blatantly violated, you're going to flag that contract as, hey, this is really bad. And then you can save that for later to actually like analyze. So for example, if there's just a contract that's leaking ether, just freely giving it out to anyone, blatantly prodigal contract, that gets flagged as a buggy contract. So then they wanted to actually validate these to get to filter out false positives from true positives. So how do you do that? And the answer to that is you actually simulate the attack on the whole blockchain. So and specifically, I mean, you download the whole current version of the blockchain and you run the attack on that target. And then you observe the result, and you just see what happens to the blockchain. If it happens there, that means it will happen on the actual blockchain. So that's how they validate attacks. Does anyone have any questions about that stuff? Because that's kind of the bulk of the presentation. After this, we're just going to go over the kind of crazy results that they found. And I'll wait for a minute. Does anyone have any questions about any of the stuff previously? Smart contracts, blockchain, Ethereum, greedy prodigal, self-destructive contracts, any of that? I can answer them happily. All right, no one? Let's move on. So discussion question, we're going to skip that. So here's the actual evaluation scope. There was almost 1 million smart contracts and almost 10,000 pieces of source code, which means there was just about a 1% instances of actual contracts with source code. They started at block 4.8 million, so that was the version of the blockchain that they downloaded. Blockchains are split up into various blocks that have these hashes that people can solve in exchange for the credits. So this was the block 4.8 million. So in terms of hardware, it was a Linux box, and there's all the hardware specifications if you are curious. So here's the results, and this is crazy. There were 31,201 greedy contracts that were flagged, and 1,524 of them were distinct. What that means is that there were roughly like pretty much 30,000 contracts that were just duplicates of each other, or like very slight variations of each other. Which means these attacks could, like the exact same kind of attack, could work on thousands of contracts, which is not good. That's not good. And that had a 69% true positive rate. That's pretty nice. Oh my god. Okay. As a result, there were 21,529 legitimately greedy contracts that you could just lock up right now, and no one could ever get money from that. And that's not good. That's bad. There were 1,500, and the prodigal contracts are the big ones. There were 1,504 prodigal contracts that were flagged. 438 were distinct, and it had a 97% true positive rate. That's really high. What that means is there were 1,458 contracts that could just give away money. You could just ask, hey, can I have some money from you? And the contract would say, yeah, sure, here you go. Here's $1,000. And that's like, you'll see the total money in a bit that could have been like stolen from these things. So here's a horrible example of the contract. Can anyone tell me why this contract is bad? You don't even need to understand like Solidity. Just look at it. Look at it for a minute.
If you have control over two different nicknames, does that?
It sets prev to nickname and checks if they're not equal.
Oh, right.
Names are just whatever you want it to be, if tap can be called by anyone.
Yep. You can just send it. You can just send ether to anyone here, because you set previous to nickname, and then you check if previous is not equal to nickname. Otherwise, I don't fully know why. But what would happen here is it would just send the whole. You could send the whole balance to the message sender. So. And this code doesn't totally make sense, does it? Because you've got previous, and then you've got previous equal to nickname in line 3. But then if previous is not equal to nickname in line 4, which doesn't super make sense.
Yeah, I think this is a weird bytecode thing where you can have two things be assigned to each other but not be the same.
It is.
Gross.
Yeah, so it's a weird, really weird thing here where you can have them assigned to the like same thing, but they aren't the actual same value. And this leaked 5.0001 ether, which is almost $10,000. So such a simple function just leaked $10,000. Or it could. I don't actually know if it was stolen. So lastly, self-destructive contracts. 1,495 of them were flagged, and it had a 99% true positive rate. and I copy pasted that wrong. That is roughly 1,481 actually self-destructive contracts. Results. Found the biggest thing here, the parity attack that I mentioned, which evaporated $300 million. They found that successfully, where every other analysis tool of like Solidity Security never had found that. So they found that successfully. 97, 69, and 99, I copy-pasted it wrong again, of prodigal, greedy, and self-destructive contracts. And this is the big number, 4,905 Ether was extractable, which is roughly $10 million as of today. Now, the problem with this is you can't really disclose this information. You can't really tell people that, hey, your contract is vulnerable, because blockchain by nature is anonymous or semi-anonymous. So how they're able to disclose this to people is not super great. Does anyone have questions about any of this? Because that was it. After this, it's just conclusion. All right. So here's a cool discussion question, and I would love for people to chime in on this. I actually want to cover this one. What do you think is the appropriate way to disclose these vulnerabilities to people before their money gets stolen? So, like, say I went today and I found a contract that was just giving away money, and it was just leaking Ether. How do I tell the person if I don't know what that account is? Or, like, if I don't know the identity of that account? Anyone have any ideas? It doesn't have to be a well-founded idea. It can really just be, just guess.
You could just inform everyone.
But yes, that's a first thought, but think about that. Let's think about that a little bit more. Can anyone tell me what the issue would be with informing everyone?
Oh, but then everyone knows what the vulnerability is.
So say I go public, like on Twitter, and say, hey, this exact contract has a vulnerability. People would just scan the contract and all the money would be gone.
Right.
So this is an unanswered question. Does anyone have any ideas? Just there's different proposals here.
Would there be like any way to allow people to discover the vulnerabilities before uploading their contracts?
Yes. That's the cool part, and we're gonna cover that. There's two fun things that we'll cover for ways to do it, and one of them is actually anecdotal, because I actually helped develop part of it, or I helped develop a security tool for it. So it's pretty cool. Anyone have any ideas about like how you could change the code to allow for it to recover from something like this, or how you could patch code like this? Can anyone, so again, with the code, code in Ethereum, I'll give you guys some hints. Code in Ethereum is immutable. You cannot change the code that gets uploaded to the blockchain, but you can change the variables on the blockchain. So has anyone ever heard of a function pointer?
Yeah.
So for those who have not, a function pointer is basically, it's something that instead of it is a function, it is something that points to a function. It's a variable that can point to a function, and when you call that variable, it'll execute whatever function it's pointing at. So the result was upgradability, contract upgradability, which basically what it did is you could have an old contract and a new contract, and then you have this upper super contract called a proxy contract. And a proxy contract would just be a list of the functions in the old contract and the new contract, and it would be a bunch of function pointers, and you could just upgrade those function pointers from the old one to the new one. So if you found a vulnerability in one of them, you could fix the vulnerability in the new version and just point the function pointer at the new contract. So it's a unique way to kind of get around that. That's very unique to code bases that cannot be changed, but the variables can be changed. So I actually worked with the company Trail of Bits last winter to help develop a Ethereum security tool, Critic, and I implemented their upgradability features into their website. I did all the back-end database and front-end stuff. It was pretty cool. But anyway, conclusion here. Trace vulnerabilities are pretty critical, and they could tear apart the Ethereum blockchain if they were abused really bad. On an analysis of the blockchain, they revealed nearly 35,000 potentially vulnerable contracts. Symbolic execution and analysis is really valuable, really anywhere, but it's especially valuable because there's a direct monetary impact in this one. And the mitigation to this is really just develop your contracts using Critic. Look at the security of them before uploading them. This is not an advertisement. It doesn't have to be Critic. Just look at the security of your contracts before you upload them. Use tools on the contracts to test their security before you upload them. There's discussion questions. There's references. Does anyone have any questions at all about this? I'm going to stop the recording right there.